come to this problem, I guess, from a physics perspective. And in physics right now, there's a lot of interest in active materials that you can think of as an agent-based interacting system. So it's actually quite more natural than you would think, maybe to extend those systems into interacting animal problems. So this work's been done by a really excellent grad student, Dan Pearce, and actually some three-dimensional work that I might talk about later by Adam Miller. And we've got a fantastic character who's an emeritus professor, George Rowlands, who we've been also talking to about this. Okay, so here's the slide. We've got, this is a very large flock of starlings, something around 100,000 birds over Denmark. And this is a very rich material, okay? So it looks a bit like a fluid. It's obviously governed by social interactions, and it's extremely attractive, to a number of communities, the idea that there might be some universality in this. And I guess to start to tackle that universality, you need to try and write down some rules for what's going on here. And most of my talk will be about the how question rather than the why question. So I'm sort of approach it, if you like, a little bit as an engineer. I want to rebuild this system. What rules should I give the agents rather than why do they have that rules? Although I'll touch on that at the end. And I was just thinking about a way of capturing the basic picture of this idea in one picture. So here it is. So this lady's sitting on the beach, and there's a sun up here, and she's getting a nice tan. And then I put some birds between her and the sun, and I want to know whether or not she's going to get a tan. And the point is that the birds here assemble to form some structure that blocks out some of the sun's rays. And it could easily block out all of the rays, or it could block out an extremely small fraction of the rays. But we're going to introduce this parameter, and you're going to see this one again later, this theta prime. This is the fraction of sky that's blocked out by the birds. So I want to invite you now to think just for a moment about whether or not you think this lady's going to get a tan, and we'll come back to that later. Okay, so why might we be interested in social systems? So we actually got interested in this whole field after reading a paper that was published a few years ago now on interacting locusts that were moving around in a track. I won't say much more about that, but it's a really beautiful paper. And we realized, of course, that this is a much more general phenomenon. It's found in fish and birds, large herds of mammals, and actually now in robot systems. And in terms of applications, I mean, I'm basically interested in this as an interesting problem in basic science, but you can also justify it if you're interested in animal conservation. That might be, I don't know, salmon farms or herds of wildebeest. You might be interested in controlling either human crowds or locusts. You might also be interested in using these systems as mimetics for swarm computing or robotics. And finally, if you've ever watched The Lord of the Rings, there's a lot of orcs that come over the hill at one point, and there are algorithms controlling those virtual crowds, and maybe we can actually even contribute to that. So how does people traditionally think about these problems? They do so by a class of models that I'm going to call local. So here's one. It's the canonical model. It was originally proposed by Reynolds, but repopularized by Vyshek. And it's a very simple idea. So you have to put yourself in the brain of this red individual here at the center, and this red individual is moving with some velocity, and it looks around it with some range, hence local, because it's only in this local environment that it interacts with its neighbors. And for everybody within that local environment, in this case these two other individuals, it seeks to co-align with them. So this is the structure of the model mathematically. It says the velocity of this ith individual, say the red one, at the next time step is a sum of two terms. The first one is an average, hence these average signs, of all of the velocities of the neighbors labeled by k, provided the neighbors are closer than this interaction distance. So this is just a local co-alignment term with some adjustable noise, which is an uncorrelated stochastic variable that just says that there's some diffusive character to their motion. And then the update rule is simple translation in time. So this gives you the spatial position at the next time step. So, okay, that's a local model, and I'll return to those local models in a minute, but there's something we should know about the data. So the first piece of data I want to show you is published by an Italian collaboration. They call it the Star Flag collaboration, and they've published a number of papers now in which they've measured flocks of starlings over Rome. Apparently Rome is a particularly good spot for this. And I'm going to show you two sets of data here. There's red crosses and the blue crosses. And I've shown them separately because they actually compute the density differently in both cases. So in one case, the density is explicitly reported, and in the other case, it's been inferred by taking the number of birds and dividing it by a linear size for the flock cubed. So that's a bit rough and ready because the flocks aren't spheres, but it's at least an estimate. So there's two things you should take away from this data. The first thing is that the density is not fixed, it's variable. Ideally we'd like more data, okay. And also there's at least a strong hint that the density is decreasing with n. The smallest densities are for the largest flocks with the largest number of birds. So the question we're going to approach is, how is this regulated? What is going on in these flocks? How is the density of these flocks fixed? And in particular, we're going to start off by asking, could it be regulated using these kinds of local models that people are familiar with? So another thing we discovered fairly early on is that these local models are typically studied inside a box. So you fix the density a priori by putting a certain number of particles in a box of a certain size. And if you do that, you can explore these models, and they've got a very rich phenomenology, which is very interesting in its own right. But if you take them outside the box, they do this. So this is a realization of a Vishek model. It's actually a slight modification in which the nearest neighbors are topologically assigned rather than with a finite interaction radius. So we've kind of cut them some slack here, if you like. And what's happening is that because of the fragmentation here, that you're getting groups that are all co-aligning with each other, but they've lost contact with the other subgroups. So the density is going to zero here. This thing is going to eventually explore an infinite-sized box. So it seems like these local rules don't regulate density because the flock can fragment. That makes sense. And the reason why the flock can fragment is, if you think about it from a physics perspective, if you've ever got finite range interactions and noise, eventually you're going to move outside the range of that interaction and get lost. So from a physics perspective, that's actually very natural. So we want to suppress fracture. So something that people have done in the literature that successfully suppresses fracture is to start with these rules, but have an assignment of metric-free nearest neighbors. So what that says is that you don't have a measurement distance. What you do is you adopt an approach something like this. Here are the birds, the black dots. What you do is you make a geometric tiling which involves dropping bisectors between all of the birds. And then you put lines across the bisectors that connect neighbors. So this is called a Delaunay triangulation. You can get rid of the original polyhedra and get left with this connected network. So this means that if you're this red one here, you can assign neighbors in a way that doesn't actually involve measuring distance at all. It's just a way of constructing a topological nearest neighbor network. So here are your neighbors. And of course, the interesting thing about this is, because you're not measuring distance at all anywhere anymore, I can do anything I like to this system. I can shrink it, and the same neighbors remain connected with me. I can shrink it arbitrarily. And I can expand it, and these neighbors still remain connected with me. So I'm never going to lose contact with these guys. But what will happen is that because it doesn't care at all about the spatial density, it's going to evaporate. There's nothing to stop these dots just drifting off. The thing will remain connected, but the actual real space density will again, in general, go to zero. So there's been another kind of way of looking at this problem, which is to say, okay, we understand that this is an issue. We need to glue it together somehow, okay? We need to stop this fragmentation or evaporation process. And one way you can try to do it is you can adopt a model that is one of a class that's known as attraction, alignment, repulsion. And here was a recent example of one of those models. And this actually comes from their paper, in which you've got a zone here with a finite range that's got repulsion of a particular form. There's another zone which is up to another finite range in which you co-align according to the kind of rules I just described. And there's another zone in which you're attracted. So the hope is that this attraction will stop the thing falling to bits. And in fact, in this model, they even further refined it to have a frontal interaction zone. We don't bother with that. So what you can do with these models is you can fine-tune the attraction. So if you very carefully choose the strength and range of this attraction and truncate the noise, and in fact also the time step, so that it's impossible to break contact, you can successfully suppress fragmentation with these kinds of models. But, there's a big but to that, if you actually simulate what you get with those models and you look at them, you get a number of things that are not terribly satisfactory. The first thing you find is that you obtain flocks that are fully opaque. So let me tell you again what this is. This theta prime is the fraction of sky that's blotted out by the flock with respect to a distant observer. So that's basically 1. The different colours correspond to birds with different sizes and with slightly different parameter choices. So you don't get a tan if you sit under this flock. It completely blocks out the sky. I'll show you in a minute why that's bad. You also get flocks that are very dense, and actually, when you look at them, they have order that's very much liquid-like order. It's got a very highly regulated bird-bird spacing distance that doesn't vary very much. This is time, this is the bird spacing, and this is time again, and the opacity. And the other thing that these models do, which is not terribly good, is that they involve updates between birds that are not visible to one another. So in this panel here, I've shown the fraction of birds that are exchanging information according to the update rule, but which are fully obscured from the birds that they're supposedly interacting with. So if you're the red bird here, you can see the first blue bird, but this second blue bird is completely obscured by the first one. 75% of, in some cases, for the larger flocks, of birds fall into this category that you can't see them. You can also ask a question about partially obscured if you care about that, and that's the case where at least some fraction of the bird is not visible to the observer, and not surprisingly, the fraction there is even higher. So these models, these local attraction, alignment, repulsion models, are not good. They have these properties in which they involve interactions between neighbors that cannot see one another. The ordering is liquid-like, which is not what you see in flocks, it's more gas-like, and they're completely dense. And in fact, although in some sense they stop fragmentation, if you challenge the system in any way, so what we've done here is we've run a number of simulations, that's all these different colored traces, and after a certain time, 250 time steps, we challenge the system by moving all the birds apart, and because they lose contact with one another, they just wander off to infinity. A model that I'm going to describe for you in a minute, which is actually our main point, is an alternative kind of model, which we call a hybrid projection model, is completely robust to those kinds of challenges. Okay, so it's also been realized that you can fix all of these problems by putting in non-local interactions, okay? In physics, we've got 1 over r squared or 1 over r interactions that are completely global and will completely glue everything together forever. So this is another approach. You can put in non-local interactions. So the kind of philosophy here goes something like this, that you've got a bird that's responding to some complex mathematical structure in which it might be computing a potential, and this potential might be a sum over all of the other birds in the flock, that's over all I not equal to itself, and you maybe compute something algebraic like this, an attraction-repulsion model where this would be a long-range attraction and this is a short-range repulsion, and then you have a sort of effective force that's a gradient of that potential. I think this is a clear example of physicists shoehorning a problem into something that they know how to solve without actually thinking about what's really going on in the physical system. And the things I don't like about it is there's lots of fit parameters, so you can see all these constants here, the A and the B, the 4 and the 2. Structural freedom, I mean, how do you even start to write down any kind of algebraic formula in an infinite dimensional space of choices? This is almost certainly not what a bird is doing. It's not computing mathematics. And the other thing, of course, that I've already mentioned is it's very bad that this sum runs over other birds, like this guy is not visible to this guy, so he shouldn't be included in that sum, but he is. Another thing it can't do is it can't explain this variable density data that I showed you at the beginning, and the reason for that is that by defining a potential like this, you basically put little springs between the birds, and the density is fixed because there's a preferred spring distance. So the preferred density is fixed by the structure of the model. And that's actually true even if you try and build metric-free versions of this. So we took a step back and asked what's really going on. And we started to approach that question by asking what does a bird typically see when it looks out from the center of a flock. So I'm trying to imagine myself being one of these little black dots for a minute, and I'm looking out. So what I'm going to see is I'm going to see a pattern against the light sky of black birds. The ones that are close to me will look like large black objects, and the ones that are far away from me will look like small black objects, and these will be tiled in my field of view. So this is going to be the primary visual data input to me as a bird. So what we're going to try and do is use that to try and put together the simplest model that uses that sensory input to generate behavior. And most of what I'm going to show you today is in 2 dimensions, but actually it really doesn't matter. It's the same in 3D, and I'll show you at the end. So here's what we do. We take a projection. We say, this is a red bird in the middle of the flock of all of these other blue birds, and for whatever reason, I've just typically indicated the size of the flock here with this circle. It doesn't have to be fixed. They can leave this circle, but I'm just indicating the size here. So, and what we do is we project out. So if this red bird looks in this direction, its view of the sky will be blocked by this individual. So I'm going to call that black. So there's a region of black in its field of view over here because it's blocked out. And mathematically, if I want, I can specify the vectors that go to the edges of that black region using this notation, just delta with a subscript for each of the edge vectors. And I can do that everywhere. So you look over here, I've got a big black region that's actually formed by several overlapping birds, and actually this one at the back, I'm not sure you can actually even see any of that one. So that's what you get. You end up with this tiling of black and white everywhere, and we can label all of the vectors with these deltas. So we want a model that takes as an input all of these vectors and generates some kind of behavior. What kind of model could you choose? Well, one choice you could say is that it likes the black bits. This red bird, it sees black bits, maybe it sees more black bits over here than over here, so it flies that way. If you write down a model like that, you'll just end up with compactification. The birds will all fly on top of each other. If you say they like the white bits, they'll just fly out to infinity and you won't have a flock anymore. There's another choice which has got some very attractive intellectual features, and that choice is that they like the edges. They fly towards the region of space where they see the most edges. And that's attractive because, as I'll say in a moment, edge detection is actually something we do very well in our neural hardware. And the information in this, the motion of this swarm is actually in some way embedded most strongly in the edges, because in the central, this black region here, the motion of the birds is in a sense only visible through the motion of the edges. So what we can do is we can say, let's construct a vector which is just the average of all of the directions to the edges. So because there are no edges down here, and most of the edges are up here, the resolved vector points in that direction. So this is just an assumption. It's the simplest thing you can do, I would argue, that couples to this projection. So if you like the idea of a projection, this is model version 1. And for free, you can take this kind of construction and compute an opacity, because from this red bird's point of view, I can just work out the fraction of black that it sees in its field of view. That's for that particular individual. And I can average it over all birds to get the opacity from the point of view of a bird inside the flock. So there's no prime here, because this is an internal opacity. It's averaged over the birds. When you see an opacity with a prime, it's what you see with your binoculars when you're looking at them from a large distance. So that's a separate kind of opacity, but they're actually closely related. So is this reasonable? I guess I would argue it is, because this is a picture of a retina. And what you're actually doing here is you're constructing the projection of these black regions onto your retina. So this projected view that you see is really directly mapped into the projection that appears on your two-dimensional retina. So what we're doing is we're taking the full three-dimensional flock and projecting it down to 2 dimensions. That's exactly what your retina does. And what's more, the edge detection that you then see on your retina is something that we're very good at doing. So this is in our hardware. So here's the structure of our model. I'll talk you through it. We call it a hybrid projection model because it involves projection, and it's hybrid because it's also got the character of these local models in it. So the update rule is that the ith individual at the next time step has 3 terms. These 2 are the traditional ones. There's a weight, so the L stands for local, and this is an adjustable parameter that tells you the strength of the local co-alignment. And this is the average of all of the vectors of your neighbors. And for simplicity, we're going to just take it over 4 nearest neighbors. You can actually generalize this to a topological construction, but the data I'll show you today is just over 4 nearest neighbors, which is an appropriate choice in 2 dimensions, it turns out. And then there's another adjustable parameter, phi subscript eta. This is a noise control parameter. This tells you how much of a uncorrelated random vector is involved in the update rule. So if this parameter is 1 and this is 0, it's a random walker. It just takes noisy velocity update. If this is 0 and this is 1, it's a deterministic co-aligner. And the new term, which is our one, is got a subscript p because it stands for projection. So this is another adjustable parameter, phi p, and it couples to the average of all of the edge vectors seen for the ith individual. So that was that red arrow that I showed you on the construction earlier, which is defined for each bird independently. So we've got 3 control parameters, 1, 2, 3. That's a very small number of control parameters for a model of this sort. If you look in the literature, you see anything between 5 and 25. The update rule is the same as before. It's just your position in space. You move in a direction which is given by this velocity, and we normalize it to make sure that all of the birds have got the same speed, v0. I'll talk about that in a moment. That's not a totally unreasonable assumption. It's very traditional in the literature. So we can also take a construction in which we say, well, actually, maybe we're not interested in the absolute values of these weights, we're interested in their relative magnitude. So we can have a sum rule like this, which allows us to eliminate this one and just construct it according to this sum rule. So this is a way of projecting the model down onto just 2 dimensions. Now the weight of the projection and the weight of the local alignment, it's easier to visualize like that. And I'll show the results in that space, where we just vary the projection strength and the local co-alignment strength, and the noise is computed by construction from this equality. Okay. So it turns out that for hydrodynamic reasons, it's actually not unreasonable that birds should have a preferred speed. If you're flying slowly, you have to do a lot of work to stay in the air, which gives you a lot of drag. If you're going very fast, you get naturally a very large drag. So there is actually this idea that there's a preferred speed is not unreasonable. So I first just want to show you a simulation of what comes out of this model. So what you have to do to run this model is you have to choose 2 numbers. You have to choose how strong you want the local co-alignment to be on a scale of 0 to 1, how strong you want the projection, the way that they respond to this projected view to be on a scale of 0 to 1, and then because of the sum rule, you get the noise for free. So there's just these 2 numbers you choose, and if you choose these 2 numbers, this is what comes out of the model. So it's a swarm, it's moving, it's not falling apart. It's not falling apart because at any point when a small group leaves the flock like this, the projected view will only have edges in the direction pointing back to the center of the flock. So they will always eventually come back and join. This is robustly cohesive. So I just wanted to show you one of those simulations, because now what we're going to do is we're going to run a lot of those simulations, and we're going to run them at all parameter values and see what we get. And the first thing we're going to report is something called an alignment order parameter. It's traditionally given the symbol alpha, and it's actually just the center of mass speed of the flock. So if all of the individuals are flying in the same direction, this thing's 1, and if they're all flying at random, it's close to 0. So what do we get for this parameter, this speed of the center of the flock, which is somehow a measure of its order, as we vary the control parameters? So remember, we've only got 2 control parameters now, the projection term, the new bit, and the traditional co-alignment. So the first thing you see is that the order, there's a bulge down here where you have high order. So these are translating flocks. They look like, if you like, migratory bird flocks. They have high order. But there are other regions of space where you have low order. The flock isn't really moving anywhere. It's still cohesive, but not moving. And the final feature I'd like to point out to you is at the bottom here, you've got a blue line. That's because if we turn the projection off, you don't get any order because the thing fragments. And I should just emphasize for clarity that each of these little squares is the result of running a simulation just like the one you just saw at that particular combination of parameter values for 50,000 time steps. So we took quite a long time to make that figure. Once you've got this idea of projection, of course, there are many generalizations you can make, and actually I'm not really going to talk about any of them except this one, and there's a reason why I'm going to talk about this one. If you're the red individual and you're not circular, and you're looking at another individual that's orientated at some general angle with respect to your direction of sight, of course, the apparent size of that individual is going to depend on their orientation. And, this hasn't come out very well, sorry, the apparent size of somebody who's short and fat varies in an opposite sense to one that's long and thin. So this guy is maximally large if he's across your line of sight. It's the opposite for the fat ones. And actually there's some hints from recent experiments on fish that orientation is important in the update rule, but that's really all that I want you to take away from that. So we can rerun the simulations just like the ones, this data that I showed you before, and we can do it for long, thin anisotropic individuals, a bit like fish. Okay, now the reason why I'm doing that is I'm going to show you some movies in a minute, and there's one phenotype that only occurs for these anisotropic individuals. So I'm going to show you all the movies for anisotropic individuals, but it doesn't make any difference except in this one case that I'll flag to you. Okay, so let's start looking in this parameter space. Let's start down here. This is a phenotype that emerges from the model that we're going to call B, and it emerges from the model around a combination of parameter values, which are the ones that I just showed you. So actually, this phenotype, a translating phenotype of this sort, we're going to call this B. And it occurs for this combination of parameter values. And we call it B because we think it's a bit like a bird phenotype. Okay, you can look in other places in this phase space. So we've only got 2 control parameters, remember. We're going to make this combination, and we're going to look to see what this phenotype looks like. This is this phenotype. We call it the fish phenotype. And it's found around these variables. And I promised to flag to you, this is one that actually depends on them being fish-like, in them having a long, thin shape. If you have them as isotropic circular objects, you won't get this phenotype. You get the others, but not this one. So we call that the fish phenotype. I don't think I really want to talk about this actually on time grounds. It can switch between translating and circulating, but let me carry on. There's another phenotype, which is this one, which we call I. This is my favorite. This has very low order. The center of the flock is hardly moving. It's not circulating, it's kind of wandering around a bit. We call this the insect phenotype. I think that looks just like a flock of midges. So that's a pretty rich phenotype space coming out of a model with 2 adjustable parameters. There's something else really intriguing that comes out of this model. If instead of looking at the order, you look at how the opacity varies, so for simplicity I've gone back to isotropic circular individuals now, what you see is that it's flat as a pancake. Okay, it's yellow, maybe a bit of green and light blue down here, but basically it's yellow everywhere. That's a very narrow band. So that says that each bird can see about the same fraction of sky, irrespective of the control parameters of the model. That's something that just pops out of the structure of the model. And what that means is that you can see about half the sky. Okay, every bird can see about half the sky, and an external observer should also be able to see a significant fraction of the sky, around a half. So a corollary of that is that these swarms, if this model is at all realistic, swarms that you see in nature, flocks of birds, should be marginally opaque. You should be able to see a fraction of sky through this flock that's about half. So this is just a random snapshot that I pulled, and of course it's noisy. Okay, this thing is not an isotropic spherical agglomeration of birds. It's got regions where clearly the opacity is very high, the image looks dark, and it's got some regions here where it's a bit lighter. But actually, I think you might agree that it's pretty striking that everywhere on that flock you can actually see sky to some extent through the flock. So it's maybe at this point tempting to think that that's a completely natural thing, that flocks have to be like that. I'm going to try and convince you in a couple of slides that that's absolutely not the case, that this is a regulated behavior. It's not just something you get for free. So the first thing we did is we went onto the internet and just did a Google search for Starling flock. And we recorded the first 40 images that we found on that search, and we didn't moderate them or chuck any out at all, except I think there was one case where it was obviously digitally doctored to look like something else. We threw that one out. We kept all the rest. And then we wanted to test to see whether these flocks are marginally opaque. Now you might be able to make your own mind up just by looking at these 6 examples, but let me talk you through the quantitative analysis that we did. We took them each in turn, starting with the first one, that's this one. We converted it to grayscale, which I think it's already done for me somehow. There we are. And we crop out everything that's not flock. So this step is just slightly, I mean, it's subjective, but it's pretty clear where the edge of the flock is. So I don't think it's too bad. There it goes. That's the flock. And then we take that image and we do a pixel grayscale distribution analysis. Here's what it looks like. So the whitest pixels are here on the scale, and they correspond maybe to this bit of sky up here somewhere. And the darkest pixels are on this bit of the scale, and they correspond probably to a black bit here where there are more birds. And we say that the lightest pixel is sky and the darkest pixel is bird, and we just ask what's the average of the distribution. This is, in a sense, the fraction of sky you can see through this flock. And then we do it for all of them. And some of the other images, this was also in the first 6 that I showed you, have a completely different structure. This is a close-up image, this is a rather distant image. And when you look at the pixel distribution, you find that there's a big spike of white there, almost perfectly white. That's these very white pixels here, and a bump right up at this end of the spectrum of almost perfectly black pixels. Those are the birds. But of course, you can do the same analysis. You set 0 here and 1 there, that's sky and bird, and measure the average opacity. And I do that for all 40 of them, and this is what we find. So this is, I think, pretty striking. They're all about a half. Maybe down, okay, there's a couple of outliers at slightly lower opacity. There's nothing above opacity of about 0.6. That's, I think, pretty striking. So I would claim that those flocks are indeed all marginally opaque. We actually went out into the field and took some data from Starling flocks, and again we found the opacity's been between about 25% and maybe up to about 50 here for this outlier. So, okay, let's say you believe that. Let's say you believe that these flocks are marginally opaque, that somehow they get to that state. Would that tell you anything about the organization? So one thing as a physicist you can't really resist doing if there's an opportunity is just to look at scaling laws. So let me talk you through what that involves here. So here's the idea. I've got the flock is occupying a piece of space about size L. I don't have to fix that, I measure it. Okay, so the birds are all contained in this size of space that's of size L, and they've got an intrinsic size small b, and there are n of them. So the density is the number of birds divided by the volume of space, and if we're in d dimensions, that's L to the d. So here it's an area density. And now, if I want marginal opacity, if I choose a random line of sight out from that any individual, then there's a zone around that line of sight that if I have a bird in it, its centre of mass of that bird inside that zone, it will block out the line of sight. So I want that to be true for about half of the line of sights I can choose, and that means I should have about one or about half birds in this green volume that I've constructed here. So the condition for that is that the density times the volume of that green bit should be about 1, say half. So this gives you a condition for marginal opacity, and we've got two equations, and we can eliminate the parameter L to see how the density scales with the number of birds, and it's like this. So the density should be a decreasing power law of the number of birds in the flock. So this is a condition that arises if you think the flocks are marginally opaque, then the density must scale like this. Okay, this is a mean field analysis. I've assumed the flock is spherical, so those are the caveats. But nonetheless, you should see a power law decreasing density with number of birds. In 2 dimensions, it's 1 over n. In 3 dimensions, it's 1 over root n. And a corollary of that is that the probability that you see sky in any randomly chosen line of sight, you can compute how that varies with both n and the size of the flock, and it crosses over from being very close to 1 if L is large, to very close to very close to 0 if L is small. And the crossover is exponential in the square of the size of the flock. That's an extremely strongly varying function. So the fact that you can see sky about 50% of the time means you're just on the inflection of this extremely strongly varying function. So I'm going to just remind you of that data I showed you earlier. I've just argued that if you believe that these flocks are marginally opaque, and we think we have data to support that, you should see a decreasing, power law-like decreasing density with number of birds, which apparently you do see. So, of course, the right way to look for power laws is on a log-log plot. So that's the same data I just showed you on the linear plot in log-log. And it's noisy, you know. I wouldn't say this is proof of a power law by a long shot, but this is a log scale, so you've actually got a substantial reduction in density. And, you know, if you do some kind of averaging, that's this curvy line, it's actually pretty close to a power law of 1 over root n, which is what you'd expect in 3D. This data set is less conclusive. And of course, there's a caveat that we've computed the density in a bit of an ad hoc way, and the flocks aren't spheres, so the scaling analysis is a bit iffy, but it's encouraging, I think, that we see this reduction of density. So we're beginning to get a picture that the data is fully consistent with the idea that you have emergent marginal opacity, and that is also consistent with our model. So let me just finally tell you about why this marginal opacity is not natural. So what I did is I just constructed a view out into 3-dimensional space, and here's a little box that I took looking out. And in that cubic box, I dropped some, it's not cubic actually, it's a long thin box. I dropped a whole load of beads that are spherical with the same radius. So the ones that look smaller are just further away from your field of view looking out through that box, through that window. And the ones that are very close, of course, appear very large. And I did it once, 10 times, with a particular spacing. It doesn't matter what the value of the spacing is, I just did it. And then I did it 10 times again where I reduced the spacing by just a factor of 2. And you find that because you're near the threshold of this very strongly varying function, you don't see any sky anymore. So if the birds move together by just a factor of 2, they basically completely blot out the sun, and that lady wouldn't get a tan. So there's no reason why the birds couldn't move together by a factor of 2. They're nowhere near bumping into each other. They're tens of meters apart, typically. So that's all because of this very strongly varying function. Now, there's a number of secondary features that our model gives that also agree with some data on anisotropy in birds and tuna, but I'm actually not really going to focus on that because I don't think it's terribly interesting. I'm going to maybe now go on and ask the why question. So we've found, apparently, that we have marginal opacity, and you can, of course, ask the question, does that relate anyway to evolutionary fitness? And we think it does. So here's why. So if you're sitting in a flock here and you've decided that your best strategy to get away from a predator is to form the densest possible flock, to get as close to your neighbors as you possibly can, you probably gain some sort of protection in the sense that, you know, it's highly unlikely that the predator will single you out, but what you pay for that is that you can't see anything. So in this case, this predator flying over here can only be seen by a small fraction of the birds that are on this side of the flock. These guys block out the view of the predator of all the guys behind them. So this is too compact. In fact, even worse, there are a couple of individuals, not only can they not see the predator, they can't see the response of the first responders who see the predator. So when these guys go nuts and try and get away, the red ones, they don't even see that. They have to wait for that information to propagate through this flock before they get that information. So that's bad. If you take the flock larger, you reach a state where a fraction of order, a half of the individuals can see the approaching predator directly, and even the ones that can't see the predator can all see the first responders. So information propagates through this flock extremely fast. And this is a marginal flock, it's in our marginally opaque state. You gain no benefit by going further apart than this because you can pretty much all see the predator anyway, and you'll reduce your protection because you'll have a much more sparse flock, and the predator will find it more easy to single one of you out. So we think there is an evolutionary reason why you might want to tune your flocks to this marginal state. So maybe we can also ask a question of the projection model. Because it's a global interaction, okay, it's what you're doing is you're taking a projection through the entire flock. There's a good chance that that might give you dynamics that are much faster and hence more realistic. Because if you look at the movie here, you see that the information propagates across this flock extremely fast. It's almost instantaneous that the birds on this side might change direction and everyone else follows. And if you've got a local model with local interactions, the dynamics are slow, and I'm just going to show you that in a very simple way. Imagine you're all lined up here, and one guy changes his mind. The guy next to him sees that, and he changes his mind. The guy next to him sees that and changes his mind. So you have to pass that information in a local way all the way across the flock, and then eventually the guy on the other end responds. This is slow. Generically, global interactions like the projection is fast. So we can test to see whether that agrees, the model gives that kind of output. And basically we find that the autocorrelation time, so what I'm showing you here is a heat map for the density autocorrelation time, the global density autocorrelation time. And in a big patch in the middle here, you've got density autocorrelation times that are extremely short. There are a few tens of time steps. So this system is responding very fast, just spontaneously in its spontaneous fluctuations, and you could expect it to respond correspondingly fast if it was challenged. Okay, so you might say, I haven't really been explicit about it, but everything I've showed you so far has been in 2 dimensions, so the models have been in 2D, although they do give this condition of marginal opacity can be generalized into higher dimension. But of course you can think about realizing the model in any dimensionality, and we've done that. So if you do a projection in 3 dimension, so these are just spheres in 3D, and I've blown up this one here to show that the projection from infinity, from the sky, that lands on the surface of this sphere generates circular boundaries. So the middle of this circular boundary here is black because the view of the sky is blotted out by that green one. The color scale is just height, I think it's not important. And the generalization before, where we had vectors that pointed to the edges of the domain boundaries in 2D, now we've got vectors that point to the boundaries of these curves in 3D. But it's a direct generalization. Now, unfortunately, I can't show you a movie of that because my computer crashed on Friday, and the student that generated these movies is away at retreat, and they don't have internet access. So I'm afraid I'm not going to be able to show you the movies, but they look very similar to the movies in 2D. And what's also important and interesting is that the opacity is similarly flat. It's around 0.5 to 0.6. The scale is terrible, sorry. It goes up to 0.6 here, and this is linear scale, so it's 0.3 here. Is very flat. So the same kind of emergent marginal opacity comes out of the model in 3D as you'd actually expect, as did in 2D. So these kinds of models look like good candidates. And finally, of course, you can play around with these systems and you can do things like put predators into them. So the problem with putting predators into these models is there's a lot of different ways you can do it. Now, the one thing I maybe just want to emphasize is that we've put a predator, that's the red arrow in here, in a very simplistic way. When it gets close, the prey just fly away from it. But what you can see is whatever the predator does, it never fragments this flock. This flock remains coherent. So if you put any kind of evolutionary fitness in this that was coupled to the coherence of the flock, these kinds of models, like this projection model that has a global interaction, will beat local models, because if you've got a local model here, the first pass will fragment the flock into 2 subflocks, and after log n passes, the predator's got one little bird that it can eat. Okay, so conclusions. Non-local interactions, I think, are really essential. It's pretty clear when you look carefully at the structure of the local models, they've got these pathologies that are really not fixable unless you put long-range global interactions into the models. So something needs to be included. We think that projection is a very natural candidate. It's natural on information theoretic grounds because it's something that you see. It doesn't include these phantom interactions. It's consistent with the physiology of vision. So we really think this is a good candidate. The simplest kind of way you can incorporate projection into these agent-based models is via this kind of hybrid projection model that I showed you. And I showed you how that can be posed in a way where it's only got 2 primary control parameters. That's an extremely small number of control parameters for a model of this sort. And yet, it's still enough to support multiple phenotypes, at least this bird, fish, insect that I showed you. And actually, there are others like this switching one that I just skipped past. Something that comes out of the model is that marginal opacity emerges naturally out of the model. So that's also something we didn't really put in by hand, but it comes out. And that's something that we think we see in data. We think these Starling flocks are marginally opaque and that that's not a coincidence. And finally, we think that although primarily this has been motivated with the how question, how do the birds do it, we can have a go at the why question too, that there may well be a connection with evolutionary fitness in these marginal states. And just to flag that we're actually currently doing some experiments that's rather exciting for me from a theoretical background. We've got a fish tank and we're playing around to try to test some of these ideas using experiments. And if I've got a moment for a little anecdote, it turns out that Freeman Dyson, the famous physicist, once was seconded in World War II to the RAF, and he was given the job of working out why we were losing so many bombers. And it turned out, although he didn't realize at the time, that the German night fighters were flying low and looking up for a contrast, a projection of the black bombers against the relatively light night sky. And actually Dyson realized this, or he didn't realize why. He realized that the data showed that when the bombers flew in a more compact formation, they were less likely to be shot down. And he went to the RAF and said, you guys need to fly closer together. And the RAF said, well, yeah, we take your point, but no, because our guys would rather an increased chance of being shot down by the Germans than a small chance of bumping into their mates. So we're not going to listen to you. So that was that. And thank you for your attention.